Okay. Hello, hello everyone. Wait a second, I am trying. Okay. So hello everyone. So I am Damien, and I am a PhD student in Annecy under the supervision of Piotr. And today I will talk about the work I did with Mehmet, Piotr, and Sasha. And so I will talk about S-matrix, Bootstrap, and machine learning. Okay, and so before discussing machine learning, I will start by a brief review of the S-matrix Bootstrap. Then I will explain our motivations for using machine learning, and in particular neural networks in this field. And then I will explain in more details how we applied the machine learning techniques in a simple Bootstrap model. Okay. So first, in this talk, I will only consider 2-to-2 scattering of identical massive scalars in 4 dimensions. And so in this case, we have the scattering amplitude, which is a function of 2 variables, s and t. So these variables, they are called Mandelstam variables, and they are computed from the incoming and outgoing momenta of a scattering process. And so there is actually a third Mandelstam variable called u, but ST and u, they are related by the conservation of energy and momentum, so that the scattering amplitude we will study, it only depends on S and T. So yes, at this point, I just want to emphasize that even if we will be focused on 2-to-2 scattering, we will not ignore a particle creation. In fact, it is taken into account by the unitarity. So I just want to say that the fact that we focus on 2-to-2 scattering is not an approximation. Okay. So now at this point, we can wonder actually what are the constraints that the amplitude A of ST must satisfy in order to be a valid scattering amplitude. And so in order to, so actually we want in particular the S matrix to be consistent with fundamental principles. So there I am talking about causality, Lorentz invariance, and the probabilistic interpretation of quantum mechanics. And so so long story short, we want the scattering amplitude A to be analytic in its in the variables S and T. We also want our amplitude to be crossing symmetric, so we should be able to switch their ST and U, and it must be a symmetry of the amplitude. And of course, we also want the scattering process to be unitary. And so now, yes, I will extend a bit on the unitarity constraints. And in particular, sorry, was there a question or no? Okay. And so in particular, unitarity, we will see two equations which impose unitarity. So the first way is to use partial waves. So the partial waves, they are computed from the scattering amplitude by projecting it on Legendre polynomials. And so you have infinitely many partial waves labeled by their total angular momentum. And what is great with this setup is that unitarity, it applies on each partial waves independently. So for each Sj, if you have the modulus of Sj smaller or equal to 1, the unitarity is satisfied. And yes, I forgot to say that in this setup, you can think of S as the total incoming energy square. So there, unitarity, it applies for S greater than 4m squared. And okay, so there is another way to impose unitarity, which is to use the Mandelstam equation. So in this case, you have a unique equation which enforce unitarity in infinitely many partial waves, since those two equations, they are almost equivalent. And so, yes, and in this talk, I will focus on how to construct non-perturbative amplitudes, so function A of st, which satisfies all three constraints: analyticity, crossing, and unitarity. So this is not the main purpose of the S-matrix bootstrap, but once you are able to construct amplitude, you can establish non-perturbative bounds on observables, and you can maybe even study non-perturbative features. But I will focus on how to construct amplitudes because it is at this step that we use the machine learning techniques. Okay, and so now I will show you two methods to construct amplitudes, each one using one of these two ways to impose a unitarity. Wait a second. Okay. Okay, so now we see two methods. So on the left, you have on this side you have the standard modern bootstrap method. So this is a method which was developed by Paulos, Penedones, Toledo, Van Ries, and Vieira. And on the other side, you have the Atkinson-Mandelstam approach. So this approach, it was proposed in the 60s, but back then, people were not able to apply this method to construct amplitude because of the lack of computing power. So I'll first give a couple of, I will first focus on the standard modern bootstrap method, and we will compare we will compare the two methods. So in the standard modern bootstrap, the idea is to expand the scattering amplitude onto in a basis of functions, and this expansion is done such that it satisfies the crossing and the analyticity constraints. And so in this case, the amplitude, it is parameterized by a set of discrete parameters, which I called there alpha ABC. And then you still need to enforce a unitarity. So this is done by solving unitarity using the partial waves. And so what is great with this setup is that the unitarity in terms of partial waves, it becomes actually linear constraints on the alpha ABC parameters. So you can, in fact, solve unitarity using semi-definite programming. And so using this method, two teams were able to derive an allowed space of a scattering amplitude in 4 dimensions. So I am still talking about identical massive scalars there. And so this result, it was derived by Chen, Fitzpatrick, and Karativ, and Elias Miro, Guerrieri, and Mehmet Gümüş. So Mehmet, who is now in Annecy and one of my collaborators. And so yes, maybe this allowed space, it is this is an allowed space, but in there, the axis, they show a Taylor coefficient of the amplitude. So there, the value of C0 at some fixed point ST, and the C2, which is the second derivative. So in particular, you can see that the Taylor coefficients, they are bounded in this allowed region in green. Okay, so that's it for the standard modern bootstrap. So now let's see what is the idea behind the Atkinson-Mandelstam approach. Okay, so there, the amplitude, it is parameterized using the Mandelstam representation. So basically, it means that the amplitude, it is parameterized by two functions, so the single spectral density and the double spectral density. And this on that, it also satisfies crossing symmetry and analyticity. And so similarly to the other method, we just need to impose a unitarity at this point. So in order to impose unitarity, you have to solve two equations. So the Mandelstam equation I already introduced, but you also have to impose unitarity on the spin zero partial wave. And so the difficulty with this approach is that these two equations, they are nonlinear equations on the function rho of S and rho of St. And so this is why those equations, they are very difficult to solve, and this is why they have not been solved in the 60s. And actually, they were solved only recently by Piotr and Sasha, but still we do not have a result similar to unallowed space yet using this method. Okay, so at this point, you may wonder why do we want to solve this nonlinear equation if we have this beautiful method which is already working and which provided great results. So actually, we would like to apply this Atkinson-Mandelstam approach to be able to describe accurately the fine structure of the amplitude. Because as we will see, the standard modern Bootstrap, it fails to describe accurately the fine structure of the amplitude. And so in particular, we can look at the double discontinuity of the amplitude. So you can take actually the discontinuity in T and in S of the amplitude, and we will look at the support of this double discontinuity. And so on this side, because of the ansatz, actually, the support, it started for both S and T greater than 4m squared. And this is not the correct support. So actually, the correct support, it is this one. It is given by the Landau curves. And in particular, it is imposed by the Mandelstam equation. So the idea is that using this Atkinson-Mandelstam approach, we are working with the double spectral density, which is in fact equal to the double discontinuity of the amplitude. And because we are solving the Mandelstam equation, we will have the correct double discontinuity support. So we basically, the fine structure of the amplitude will be better described by this approach. But we have to solve a nonlinear equation, such as the Mandelstam equation. Okay, so now let's see what has already been done using this Atkinson-Mandelstam approach. So as I said, in 2023, Piotr and Sasha, they managed to impose a unitarity. So they solved the Mandelstam equation and the equation in the spin zero partial waves. And they have done that using a fixed point iteration method. So this is great, but the issue with the fixed point iteration method is that it only converges when the fixed point is an attractive fixed point. And so in fact, this fact, it does not depend of the existence of a solution. So it's for some solution, the fixed point iteration method will diverge even though there exists a solution. And so well, you could try another method to solve unitarity, the unitarity equations. For example, you can try to solve the Newton's method, but actually you will encounter the same kind of divergence issue. So the Newton's method, it can also diverge even if there exists a solution. And so for some times, the status was as follows. The Atkinson-Mandelstam approach, it could only be applied in a small region near the origin in this space, and it was the only region where the fixed point iteration method could converge, even though we knew already that there existed a solution somewhere else. Okay, and so actually it is sorry, I'm just looking at my notes. Okay, and so it is in order to solve this convergence issue that emerged the idea of using machine learning techniques to solve these linear equations the Mendelssohn equation and unitarity. And in particular, we will use a neural network. So okay, so now we would like to test our new method based on the neural network. And instead of solving the full problem immediately, we experimented with a simpler model. So, and yes, from now, everything I will say is based on our paper available on arXiv. So we obtained a simpler model by setting the double discontinuity or the double spectral density to 0. So it's an approximation. It's in order to experiment our method. And so in this case, the Mendelssohn equation no longer makes any sense. So we do not have this equation. But we can still solve unitarity in the spin 0 partial wave. And well, for simplicity, we replace the inequality there by an equality. And so this equation, it is actually an equation on the single spectral density, rho of S. And now I will write this equation as follows. So rho of S is equal to phi of rho. So, okay, so this setup, first, it's a non-trivial problem. So this equation, it is still a nonlinear equation. And quite importantly, the fixed point iteration and Newton's method, they still diverge in some parts of the allowed space. So we will be able to check if using our neural network method, we can find new solutions which were not reachable using these methods. So yes, this is a good setup to check our neural network method. Okay, so I want to emphasize that quite importantly, we do not rely on any external data. We are doing unsupervised learning. And in the next slide, I will just show you the key steps which allow us from this functional equation and the neural network to obtain a solution to the equation. And in the next slides, then I will explain in more details our implementation. Okay. So for now, we will just assume that we have a neural network. And in this case, it will be a function of a single variable. So in this case, S. And this function, it also depends on a set of tunable parameters, sigma. And so when you have a neural network, you can train it. And so in this context, by training, I mean that we can adjust the parameters sigma in order to minimize the quantity, which is called the loss. And so we have we have a neural network, we can train it, but we have to define a loss, a quantity which will be minimized. And for example, we can choose this expression for the loss. So the neural network minus phi of the neural network squared. And we integrate over from 4m squared to infinity. So actually, we are using the unitarity equation and we are minimizing left-hand side minus right-hand side squared. And we want to minimize this quantity. And so in particular, this loss, it is minimized when it is equal to 0. And then the neural network, it actually satisfies the unitarity equations. So basically, we have our neural network, which is our spectral density. So this will be the main idea that we will apply. But, okay, so no, this will be the main idea that we will apply. And so in the next slides, I will explain how we constructed our neural networks, what is the actual loss that we used, which is slightly more complicated than this one, and how was the training performed. Okay.
Sorry.
So
I have a
yes.
question. So you could have also added some, I don't know, some weight that depends on S, well, on V. Would
Yes,
that change anything?
Yes, actually, we use the weight, and it would give more penalties. So first we used one, and if you give more weight to a given energy range, you will solve unitarity with a better precision at this energy range, because the penalty of unitarity violation will be better in the loss, will be greater if you have a greater weight. Okay, did I answer your question?
Yeah, thanks.
So
Okay.
another question. So how many hidden layers do you use in the neural network? Or
yeah, I will explain that in the
okay.
next slides. Okay. So first, so I will define what is a neural network. And so in our case, we will build our neural network from two kinds of layers. So linear layers and activation layer. So the linear layers, they takes as an input a vector, and they multiply it by a weight matrix, and they add a bias matrix. So the component of the weights matrix and bias matrix, they are what I previously called the tunable parameters. And yes, the input and the output of this layer, they can have different size. So there, the W matrix, it can be a non-square matrix. So the other kind of layer used to construct the neural network is the activation layer. And so it applies an activation function to the input vector element-wise. So its role is to bring nonlinearity to the neural network. So there are many possible choices for the activation layer. The most commonly used is the RLU function, which is a max between 0 and x. In our case, we used the CELU function, but I will skip the details there. And so then the neural network, it is built by alternating a linear and activation layer. And so since a linear layer it is always followed by an activation layer, I will group them in this orange block. So for example, we have there a simple neural networks. And well, in our case, we will only use neural networks which takes a scalar as an input, and for which the output is also a scalar. But at any intermediate step, you can have a vector. Okay. So now I presented you the neural network as an alternating I constructed the neural network by alternating between a linear layer and an activation layer. But this is actually completely equivalent to the picture of the neural networks in terms of neurons. It's just two ways to express the same thing. And quite importantly, the neural networks constructed this way, they can approximate any functions. So this is a consequence of the universal approximation theorems. And so the bigger is the neural network, and yes, the better will be the approximation. But a consequence of these theorems is that you can always parameterize your function by a neural network. If the neural network is big enough, it should work well. Okay, and so in our case, we will want to parameterize our single spectral density with the neural networks. And so first, we have some analytical results for our spectral density. So we know that for s close to 4, it behaves like a square root. And we also know Ricci expansion. So we know that it decreases very slowly with at high energies, like 1/log square. And so we can take into account this knowledge when we parameterize the spectral density. So there I am defining a rho of sigma, which is a square root of s minus 4 multiplied by the neural network, and we divide by 1/log of s square. So actually, the fact that we put this prefactor, it really helped the neural network during the training phase, and in particular this square root, because it in fact, it imposes the boundary condition at s equal 4 and s equal infinity. So this can really help during the learning process. And so for numerical reason, yes, we used for the neural network input 4 over s, which I call x. So x it belongs to 0, 1. Okay. So I said that there is a Rege expansion or a high energy expansion actually. And so this suggests that the spectral density, it has two regimes. So one intermediate energy regime and one high energy regime. So this high energy regime, we expect it to be valid at exponentially high energies, since rho it decays extremely slowly. So we expect something like it is valid for s of order 10 to the 20, so x around 10 to the minus 20. And in fact, at this point, we also would like our neural network to describe the spectral density in both regimes. And it is to achieve it is in order to accurately describe both regimes that we use this architecture for the neural networks. So it takes two inputs, x and log x, and the two inputs, they are going into two sets of independent layers. And so the idea behind this architecture is that when x will be extremely small, so order 10 to the minus 20, for example, and if you keep increasing s, then the output of this set of layers, it will basically remain constant. While there, the output of this other set of layers, it will vary as x vary. So the idea is that this part of the neural network, it will be able to learn the Rege behavior, while this one will be able to learn the intermediate energy behavior. Then these two neural networks, they are mixed in 3 more sets of layers. So in total, we have something like 9 linear layers in our neural network. And we have a width of 128 at the maximum width it is achieved in these layers. Okay. So now we have our neural network and the way we parameterized the single spectral density. So now
I have a question. So in principle, I guess you could have just blindly asked the neural network to approximate the full function without splitting the log part and the x part. I mean, I guess that you did it this way because it works better. But how does it work if you do it just blindly, and how was did you try many things?
In fact, so we are using Python to implement our neural network. And so in particular, we have a finite precision. So we have only a 16-digit precision. So we are using float 32. And so if we do not use this trick, well, the computer, it cannot make the difference between x equal to the 10 to the minus 20 and 10 to the minus 100. So in this case, actually it works. You can really solve unitarity in the intermediate energy regime, but you cannot see the Rege expansion, which is known. So we used this trick really in order to be able to see this Rege expansion.
I see. Thanks.
And well, also it turns out, in the end, I won't have time to explain that, but the high energy is really relevant when we wanted to find the allowed space for this toy model, but maybe I won't explain this. Okay, are there other questions? Okay, I will keep going. So, but yes, in conclusion, this is only to see the high energy, but the fact that we that we fixed the boundary condition, it really helps the neural network during training. If you just set rho equal to the neural network, the training, it won't always manage to find a good solution. Okay, so now, yes, I will show you the actual loss we used. So the unitarity equation we are trying to solve is this one, so unitarity in the spin zero partial wave. And so the loss we used is this one, so S0 square minus 1 and everything squared. So there, inside there is the dependence, there is the neural network inside S0. And indeed, so we used a weight factor in our case in order to give more weight at the high energy behavior. This was still to force the neural network to learn the Ricci expansion that I showed on the last slide. And yes, so I have to, in reality, we could not compute integrals. So in fact, we use a sum over S for numerical reason. So we have a finite grid of points, and so we imposed unitarity for energies between 4m squared and 10 to the 100 m squared. Okay, so now so we have our loss and we have our neural network. And so now during the training, the parameters sigma, they are adjusted iteratively by a gradient-based optimization algorithm. So okay, in our case, we used the Adam optimizer. As I said, it is a variation of the standard gradient descent, actually. And this optimizer, it is provided by the Python library PyTorch. So this is a library we used to implement our neural network, and the Adam optimizer is one of the most used optimizer to train neural networks. Okay, so how does the training goes? So as I said, it is an iterative process. So each iteration, it begins by computing the loss and the gradient of the loss with respect to the parameter sigma. So this is the gradient of the loss with respect to sigma. And then the optimizer, so in our case Adam, it uses the gradient to update the parameters of sigma. And so the loop, it continues until the loss reaches a plateau. Then we can stop the training since the neural network is no longer learning anything. And so in our case, the training, it lasts around 10 minutes on a standard laptop. And the loss, it plateaus around 10 to the minus 6. And this corresponds to having our spin zero partial wave equal to 1 with equal to 1 with a precision of 10 to the minus 3. Okay, so now I will show you an example of an amplitude we could get using our neural network. So we will first look at the right plot. So there the horizontal axis is 4 over S. So the high energy is there around 0. So first, if we look at the modulus of the spin zero partial wave, you can see that it is indeed approximately equal to 1 everywhere. So we indeed imposed unitarity. And I am also showing the real part of the partial wave and its imaginary part, so respectively in red and in blue. And well, we can observe that there, the phase of S0, it is quickly rotating. So this is physically, this corresponds to a resonance. So it is so the neural network during the training, it has learned that there must be a resonance around this energy. But well, this is quite common in the S-matrix Bootstrap. Then when you impose analyticity, crossing, and unitarity, it generates resonances. So there we could see the intermediate energy, the intermediate energies. Now we will look at the left plot to see the high energy. So there the horizontal axis is S in log scale. So in red, I am showing the imaginary part of F0. So in fact, it is proportional to the spectral density. And in gray, it is the first term of the high energy expansion. So you can see that the red curve, it is closer and closer to the gray one, even at 10 to the 100, the second term of the expansion, it is still relevant there, since the two curves, they do not match perfectly. Okay. So, well, as I showed, we are able to impose unitarity both in the intermediate energy and at high energy. Because yes, what I forgot to say, sorry, is that this Ricci expansion in gray, it is a consequence of unitarity. So the fact that we agree with it, it means that we are indeed solving unitarity, even at high energy. Okay, so now we are able to construct amplitude, and we can wonder if we can reproduce an allowed region, something similar to what to the result I already showed you. So we'll try to reproduce this kind of result with our neural network. Well, actually, we do not expect to find the same region for the simple reason that in our case, we have a zero double discontinuity. So our amplitudes, they are unphysical. This is a toy model, basically. So we will find something smaller somewhere in the green region. So in order to find the allowed space, we would like to be able to move in this plane, so in the C0, C2 plane. And so we want to be able to fix this Taylor coefficient in our setup. So actually, C0, it was hidden in our unitarity equation all along, so we can just choose it. This is not an issue, but it's not the case for C2. So we have to find a way to impose a value for C2. So actually, C2, you can compute it from the spectral density. It is completely imposed by the spectral density. So one simple trick we can use is to add a new term to the previous loss I showed. And so we will, this term, it is the current value of C2 computed from the neural network minus the target value that we want. And so this term of the loss, and yes, of course, everything squared. And so this term of the loss, it is minimized when the value of C2 computed from the neural network is equal to the target value. So now we can fix both C0 and C2. So we can try to solve unitarity for every single point in this plane, in this C0, C2 plane. Okay, so now, so I am showing there the C0, C2 plane, and in purple, it is the region where we were able to solve the unitarity equations for our toy model. And so, so this purple region, it is we are restricted to the bottom right of the full green region, but well, this is expected. It's a consequence of our approximation, the fact that we have a zero double discontinuity. Now, there are two important facts. So first, in red and in orange, I am showing the area where the fixed point iteration method and the Newton method converge. So one important conclusion is that we are able to solve unitarity in a much bigger region than what was possible before using these two methods. And the second thing, so this purple region, we were able to find it using the modern standard Bootstrap approach. And it completely matches the region we found using our neural network method. So actually, this purple region, it is the biggest region where you can solve unitarity in the spin zero partial wave while having zero double discontinuity. So we cross-checked with another bootstrap method. Okay. I think I did not forget.
I have a question. So what happens? So yeah, you have this now new loss function, and so if you put a value of C0 and C2 that is outside the purple region, it just doesn't minimize it to 0. It's this that happens, or what happens?
Okay, very good question. So actually, it's a bit tricky. First, yes, if you choose C0, C2 far away from the allowed region, yes, the loss, instead of being very small, it will be of order 1. So that's definitely that the unitary is not at all imposed. Now, close. Okay. Now, first, do you remember this regex expansion? So this is a consequence of unitarity, and it imposes that the spectral density, it imposes that it must decrease with high energy. And actually, what happens if you try a point right outside the purple region? In fact, we could not find an amplitude with a decreasing spectral density. So the amplitude, it was starting to grow at infinity. So actually, it has very little impact on the value of the loss. So just looking at the value of the loss, you could not really see if you are inside or outside the allowed region. But if you look at the Regge behavior, which is a consequence of unitarity, then we were able to detect the boundary there.
So if you didn't put this logarithmic piece in your neural network, you would be screwed.
Yes.
I see.
And so this is why we cross-checked with the modern standard bootstrap method. But so actually, yes, the modern bootstrap method, it is actually the good way to find a allowed region, I would say. The goal with our method is more to be able to study the fine structure of the amplitude. So the two methods, they can work hand in hand, and then we avoid this kind of issue.
Thanks.
Okay. And so now I can conclude. So actually, what we've done is that we successfully used neural networks to solve nonlinear equations. So in our case, we used the neural network to impose a unitarity in the spin zero partial wave. So we were able to impose unitarity from low energy to very high energy, so 10 to 100 m squared. And we also were able to find an allowed region for our toy model. So the next step is indeed to solve the Mandelstam equation. So in this case, we would have to parameterize the double spectral density with a neural network. And if we manage to solve this equation, we would be able to study so the impact of inelasticity and the allowed on the green allowed region, and maybe even study rigid trajectories, which seems to appear in some part of the allowed region. So one last comment. So what we did, what I explained in the talk is how to build amplitude, and it enables us to find an allowed region, but you can also use analyticity crossing and the unitarity to find the exclusion region. And so this is called the dual approach. So I just want to mention that we were able to apply this dual approach using a neural network. So we did that by minimizing the dual Lagrangian with parameterized by our neural network, and we were able to find results which match the other's dual approach. And Okay, yes, I think I can stop now. Thank you for your attention. There are still questions.
Yes, maybe I have a question. So at the beginning, you made a point about the fact that solving the amplitude through the Atkinson-Mandelstam equation required some non-linearities, right? Do you see the impact of these non-linearities in the toy model that you studied, or
Toy model? No, not really. For it is sure that it will be visible for the full problem, because there we will have the support of the double discontinuity, which will be different from the standard bootstrap method. But yes, for the toy model, no, it was not
I see.
the impact of the nonlinear equations. But maybe I can emphasize that in our case, we were able to better describe the resonances with the neural network compared to the other bootstrap method. So you can see that we still have small wiggles where the phase of S0 it rotates quickly, but using the other method, you can have a huge inelasticity there. So we were able to resolve better this kind of resonances.
Thanks.
Can I ask a question? Okay, very nice presentation. I saw your paper earlier, so I have a few questions. Just a curiosity. Do you think it's possible to build the neural network such that you get all three symmetries, all three constraints already built in the network?
Somehow, no, I don't think so. That's the short answer. But yes, you could try to have a neural network which is analytic in its input. So it actually depends on the. Sorry, I lost. I'm completely lost. It depends on the activation function you are using. This activation function, it is not differentiable. We used one which was differentiable, but actually, no, I think it's very difficult because in this case, the amplitude, it has a branch cut at specific location, etc. So I doubt it is possible. Yes.
Okay, thank you.
Sorry, is there also, can one do a toy model in 2D? Or this is too trivial?
Actually, we also did the exercise in 2D. It's not even a toy model. Actually, the 2D setup, it already looks like that. So you would solve exactly the problem. Well, so it's basically it's the same problem. This is equivalent to the 2D problem, yes. And we did that, it worked, and we were able to access a solution with only one CDD pole, so where the fixed point and Newton were failing again.
And that, how does it compare with the usual, usual technique?
With the usual technique. So I said, if you try to solve it. Okay, so in 2 dimensions, we did not try to find the allowed space. We jumped quite quickly to the 4-dimensional problem. But maybe you can be more precise in your question. I'm not sure I understood.
I mean, let's say that a typical 2D case, you would have, okay, you have both dual problem or primal, but I mean, you have some standard techniques to deal with this matrix bootstrap. And you're doing it instead, for what I've understood, with some neural network also in 2D, no? And so how do they compare the previous method and the neural network? Can you get better results? I know, for example, one of the problems in 2D was that there was this saturation of unitarity. Can you, and I mean, I thought that one of the ideas was of actually using this non-linear equation was to actually introduce some sort of particle production. Can you actually build something new, or I don't know, like what are the results, let's say, compared to the previous ones?
So first, in 2D, we only tried to solve this equation, so which saturates unitarity. We can compare the result with the known CDD factors, and so actually yes, in 2D we know the analytical results, so we can compare and we can check that it matches well, and the neural network method it also worked when the fixed point and Newton method was failing in 2D. So this was for when there was a unique CDD factor. And about the inelasticities, that's indeed something we tried in this setup in 4D. So we can just use a slightly different loss, which do not impose a unitarity up to infinity, but up to the multi-particle threshold. And well, in this case, we would have inelasticities at high energies. So yes, that's we can have inelasticities. We just did not try in 2 dimensions. Did I answer your question?
Thanks. Yeah, so I wasn't understanding that you were setting S to 1. So okay, you were just checking. You were getting some integrable results, some CDD factor, some. Okay. But yeah, I guess my question was how fast it was getting it with respect to the usual methods, but probably they are both fast. I don't know.
Did it a long time ago. I don't remember the time compared to the iteration method, but so yes, I don't remember. But yes, it was quite fast, like on a laptop, at most 10 minutes.
Thanks.
So I have one question. In the case in which you mentioned that it was more difficult to exclude solutions that were close to the what color was the purple? Yeah. Yes. So, but for those, if you take that solution and you check for the positivity of the partial waves, that it works, or you need to go higher order in the partial waves? Because you mentioned that you exclude it by looking at the rigid behavior, but could you do it also from the partial waves, or it too expensive to look at those?
Not mentioned because it would be too complex. Actually, we imposed that the output of the neural network was positive. So that actually positivity is already satisfied. And so, no, actually, I think it was the only criteria which enabled us to find a consistent boundary. Okay.
Thanks.
But sorry everyone, by the way, I completely missed the time. I'm on the West Coast and I could have been there for 6:30, but I thought it was 7:30. One more thing, Damien, if you're with your growing behavior that you exclude, logarithmically growing behavior, which you consider as pathological, but as being above the limit, eventually it would violate unitarity. Except you don't see it at 10 to the 100, maybe you would see it at 10 to the 500 or something like this. I don't know, but
I see.
is that correct?
Is extremely slowly with energy, the 1 over log square, so it does not yet impact the loss. But of course, yes, if we were able to reach extremely high energies, we would see the effect of this growing behavior.
I see. Thanks. So are there any other questions for Damien?
Just a small one. So when you say Newton's method doesn't work, so it means the sort of region of the initial guess from which then it's convergent, it's too small, and then practically it's not useful? Or did you mean in another sense?
The orange region, it is obtained, yes, by you do not outstart, you start for a constant solution, and it is able to find a solution. So then, yes, if you outstart on the neural network, the Newton's method, it can converge. So actually, it seems random, the area where the Newton's method converge when you outstart on the neural network. But still, you are lacking a huge piece of the allowed space. But yes, it's a bit more subtle, the Newton's method. Where does it converge? It depends on how you start, etc. But
Thanks.
we could observe that there is an eigenvalue close to 1, so we could not find any solution close to this point, so that's for sure.
Thanks. And can I ask you another quick one? Have you tried any case where you have a nonlinear equation and maybe it's a case where you know there are two solutions? In that case, is the network finding like two alternative sets of weights?
It is the case for our setup. So there we only impose a C0, but in fact, there are infinitely many solutions when you fix C2. And so actually, when you impose just a C0, well, the neural network, it could converge a priori anywhere there on the line. But in our case, what happens is that we were always finding the solution on this lower boundary. So maybe because it was simpler, there was no resonance. Well, I guess it depends on the setup. In our case, we always found the same solution, even though we knew there was infinitely many possible solutions.
Hey, interesting. Thanks.
There's a question in the chat.
Comment on the hyperparameter tuning for the network. I'm not sure I understood.
Yeah, I just wanted to ask, how did you decide on the number of layers and the number of, so you mentioned that the dimensionality was 128, I think, on each of the layers. So I was wondering if you played around with the structure more to see how the performance changed.
Actually, yes, in order to fix the size of our neural network, we just, the short answer is that you have to try and you increase the size until it works. I ended with nine layer because this was the length where the neural network was consistently catching the right Reggie behavior. And maybe I can emphasize that in general, you prefer to increase the depth of the neural network. So you prefer to add layer than to increase its width. But I'm not sure I can do very general comments about that. Do you have a more precise question or?
No, yeah, because generally when you're trying to construct these neural networks, you have to kind of have some intuition for what kind of things you're trying to learn, and then depending on that, you decide on, okay, how many layers, what kind of architecture you want. And so similar to the question you answered earlier, right? That, okay, for the log behavior and for the other one, you need these two pieces, right? So you had this intuition to, tell you how to design the network. So I was asking for, more comments along those lines. Yeah, but I think you answered my question already. So yeah, thanks.
Sorry, I just have a question about what you said earlier. I think the previous question, the question before Volkit. So you mentioned that the loss along the. Could you go to your phase sort of diagram? The last slide. Yes, that one, this one. So you mentioned that along the vertical, the y-axis, the loss function always has the same value, right? But you always found, at least that I don't know if this is true, but you always found the solution that is at the border.
Yes, the loss is 10 to the minus 6. It mostly depends on the value of C0. So when you increase C0, the loss it's grow slowly.
It's around 10 to the minus 6, but it's not always the same. That's what you mean. Okay.
Yes, so there it's more 10 to the minus 8, and it becomes maybe slightly closer to 10 to the minus 5 around the tips, but
okay, so it doesn't change as much with C2. Okay.
No, with C2, not that much.
Okay.
But that, for example, you could put some weight on the part in front of C2 and get the much, let's say, or put a different function instead of just a squared. Yeah, to make it more relevant, no?
Yes. Yes, I forgot to precise, but there I can put the weight on any side. But yes, actually we use a weight there so that this is much more relevant at the beginning of the training. And well, we were able to fix C2 with something like 2 or 3 digits, precision of 2 or 3 digits. So it was fine the way we fixed the C2. Well, I hope I answered both questions. I'm not sure.
Okay.
So the time.
If there are no further questions, I have one for the Michelangelo.
Yeah,
He's here.
So let's thank
Damien.
Damien. Thanks, Damien.
Yeah, thank you.
So about this maximal transcendental principle that you mentioned, is that proven? Is that understood, or?
But not really. I guess is something that was noticed by LAPTh in the 90s and is holding in some cases. For example, in this case, for the Pomeroy case, the leading order is exactly the same. The subleading order is matching, but the sub-subleading, we have a result from integrability, but there is no result in QCD. So yeah, there are not many data points that you can really trust, let's say. But it's also true in some other context, I guess, in amplitude context, in which they found some match. But in that case, just 2 data points, let's say.
Mm.
And one interesting point could be, now that we know that Oderon is measurable, and in principle, we can know leading order in G in principle, could be interesting to understand where Oderon is in unequal 4, because it's not just a twist 3 local operator that I was showing. It's probably some, I don't know, interplay between different operators. Remember, the Oderon is like the difference between proton-proton and proton-antiproton. So it could be that in a light array operator's point of view, could be that is the difference between 2 4-point functions in some sense. But it's not really understood now.
Yeah, other thing that I wanted to ask is about non-planar corrections. I guess you only compute planar corrections because you're doing integrability.
Yeah.
And it's for this twist for this BFK for this leading family, I guess that's only relevant at 4 loops that you start to get non-planar corrections. What about for the other one, for example?
Let's say, like looking at this problem from integrability, you really don't care much about non-planar correction because they are unreachable. So let's say,
right, but yeah, but if you want to compare or to compare with QCD, I guess.
yeah, sure, I agree.
Yeah.
I mean, the most one interesting point is the most transcendental part in the QCD result doesn't depend on 1 over NC. So the part that depends on NF, the number of flavors and the number of colors, is a sub-transcendental. For example, the next to leading order is the zeta2 term. So it's the pi square term, if you want, that is depending on this. So integrability cannot see it, and the maximal transcendental principle is not really touching them. So in some sense, you can avoid this part. But obviously, if you want to have the complete solution, you have to go subleading in N, but it's totally unreachable in N equal 4, I guess. Because also you will never have like some number of flavor over number of colors kind of behavior.
Yeah.
SUN, a part of like in principle knowing all of the SUN -1 and -2 and so on.
Yeah, I also have another question. Yeah, you showed that there's some solutions that start at weak coupling with some strange behavior.
Yeah.
Well, not strange, but okay, you understood it.
Unusual, let's say.
Yeah, unusual. So, do you expect something similar at strong coupling? Or
No, because For in all the cases, so I never spoke about strong coupling, but
Right,
from
yeah.
this, obviously we can go very strong coupling and we can fit data. And there are also other papers that are looking at from the integrability point of view directly from strong coupling. And you just see the usual behavior. So square root of lambda to 1/4, if you want, plus subleading terms that goes as a 1 over square root of lambda. So everything is fine, let's say, at strong coupling. All of them, they behave in an expansion in a series of 1 over square root of lambda, as expected.
Okay.
And also, I have to mention this stuff because the two behaviors are very different. Because when you are strong coupling, let's say the horizontal trajectory, the trajectories are bending and they grow and they move away from the horizontal trajectory. When you're going weak coupling, you see the degeneracy. So the problem of this linear G term is the fact that you have this very strong degeneracy depending on trajectories you have on the horizontal one. And this is happening only at weak coupling.
Thanks.
No worries.
So maybe I have also a question for Michelangelo. So you showed that there is a polynomial in omega. Do you remember correctly?
Yeah.
Was what's the origin of that polynomial? I mean, is there a group theory origin for that, or you just do it?
No, let's say it's just
Let me see.
if you go very close to this branch point, you have two different behaviors, no? The horizontal one and the diagonal one. When you zoom in very close to it, you can expand in terms of the pole that you have at the branch point. And you can see an expansion in terms of powers of 1 over omega. Omega represents the pole. This is given by rearranging the result that we have very close to the branch point. It's just rearranging the power series. The stuff that you can notice there indeed is like the curious stuff that I was showing is how the leading behavior is similar or not exactly the same of the one loop anomalous dimension of the related operator. That is very untrivial and very unknown. We don't know even where it's coming from. But yeah, the origin is just the result from these asymptotic Bethe-Baxter ansatz rearranged close to the point. This suggesting also that probably there is another way to simplify all this quantum spectral core business just at that point. And so to re-expand all your delta or S, if you want, in terms of this 1 over omega expansion. And this is showing like the leading pole that you have in BFKL in some sense.
I see.
Can I ask something to Francesco? From your talk, was delayed formulating the question. I was thinking about your talk and the interaction between the coherent state with the light state. And in heavy light bootstrap, the main observable associated is the double trace, the heavy light double trace. And since you show the geometric series appearing with a low eta expansion, is that then the decimation should only depend like on the first diagram, right? So are you expecting this behavior to also appear in, for example, the anomalous dimension of the double trace, this decimation, this geometric series on the anomalous dimension, on the expansion of the anomalous dimension in small eta?
Okay, yeah. So if you look at the CFT data for operators exchanged in the individual multi-particle correlators, as I mentioned in the talk, you get the diagram that contributes also to the heavy light, but also other diagrams. And those other diagrams, in principle, there is no reason why they should exponentiate or belong to any pattern that you see from the HH light correlators. So in this sense, no. But it's curious, and I don't have related also to the question of Marco. There should be somehow the HH, the heavy light correlator is telling you that maybe you should try to organize the CFT data, let's say as function of spin, in some way that respects this kind of division of diagrams in a way. But I don't have a better answer. I mean, it's a work in progress, so maybe in the next.
Yeah, of course. I do have another question,
Yes.
if I may, is that you also mentioned solving the wave equation in the curve geometry, and this is just some intuition for me. It was very hard to imagine. So the connection, because usually I imagine a wave oscillating around a very heavy object, and it's hard to connect this with the idea of a double trace where you have two particles which are orbiting each other. What's really the connection? How does one draw it?
So I think it's not just the double trace. The double trace are the first one that you would.
Yeah, it's the first one. Yeah.
This correlator really gives you access to higher traces CFT data. So, for example, it allows you to prove that you find 3-point functions of light triple particle, non-protected triple particle. There must be they are non-zero, they are order 1 over n. So this is it's a neat computation that you can do by reasoning by contradiction. So you say if those are not there, then I can deduce everything from the double traces. And then you go in the correlator that you computed, then you try to check whether this is true or false, and you find that it's false. And it's false because you forgot about adding the contribution from the triple traces. And so, for example, it tells you that, as I was saying before, triple function of light triple trace is 1 over n, but also light square triple trace is 1 over n, and the two are not related by any kind of they're the leading contribution in both cases, but they are not related by any proportionality, which is simply a factor of 2. Let's say if you were imagining some kind of disconnected, so say in the case you have 2 square triple trace, you could imagine of getting rid of a 2, kind of factorizing it, but it doesn't work. So it's really a new piece of CFT data which is connected, and
yeah, it's much richer than I was picturing. Much simpler. Yeah, thank you.
Can you connect with the recent work by Peter Kravchuk and Jeremy Mann?
Good. I should study more in detail what it's a long paper. I didn't get exactly the time to but maybe yes. Yeah, maybe yes. But you should connect more directly to, if you take the 6-point function, Vasco, of 602s, there should be some kind of relation between that, or maybe even 5.5. Yeah, 602s would be connected to the multiple correlators with O2 to some power, O2 to some power, and O2, O2. But there are also other families of multi-particle correlator that you can study, like O2 to some power, O2 to some power, and then other particle, O3, O2, O3, or other stuff that could be directly related to 5 points also, OP limits of 5 points. So maybe something I didn't mention in the conclusions. It would be also nice to understand whether there is a meaning of the flat space limit for these amplitudes, because mathematically you have an amplitude, so you can do it, but physically it's a bit like it's a little bit unclear, because you have now your state is a double particle. So is that a well-defined wave function when you take the flat space limit? That I don't know.
So are there more questions for today's speakers? So if not, yeah, I would propose to close the session and then return tomorrow.
Yeah, let's thank everybody for participating. Great talks. Thanks, Michelangelo, Damien. Thanks a lot. So tomorrow we have a first session in the morning with the review talk by Vladimir Brown, and then similar group presentations and discussion in the afternoon. So I hope to see you tomorrow and send a reminder in the morning.
Thank you.
Thank you. See you tomorrow.
Bye. See ya.
And see you.